Hello everyone. Welcome to the masterclass on ChatGPT architecture. So far, we have so many candidates. Okay, Amina, let me start the chat. Let me see how I can do that. Start with that. Okay, can you try with the chat? I guess it should be working now. So yes, okay, now it's working. Hi, Vina. Yeah, Monisha, chat is on. Actually, yeah. So hi, Monisha. Hi, Amina. Nice to meet you. So feel free to use the chat window and the Q&A window. Like if you have joined through YouTube, you can ask your questions in chat. So we will take up the question based on either we will take it on the last. Like we have a separate time dedicated for the Q&A only. So we'll either take it at last, or we can also take some questions in the between. Like not all the questions, but yes, surely some questions. The same goes for Zoom chat also. If you have joined through Zoom, then please use a Q&A window to ask the questions, or you can also use chat. So both options are there for you, whichever you feel preferable. So in okay, let me share my screen then. Just a second. Okay. So this is our topic for today, which is ChatGPT architecture. Wait for some more time, and then we can start. I guess 1 minute or so. So some candidates are. Yeah. So yeah, I guess there are. Hi, Prince. Nice to meet you. Okay. Okay. Let's start then. So today we'll covering the ChatGPT architecture in detail. So we'll cover everything in a step-by-step manner. We will start from the very basics of machine learning and we will jump on to the ChatGPT architecture. This presentation or masterclass is ideal for both technical and non-technical persons because we explain everything from scratch. We explain everything from beginning. So, although there will be a little math involved, but believe me, you will get everything. So, I guess now everyone already knows ChatGPT. So, ChatGPT is although a chat interface provided over GPT model. So, we'll see this in the lecture too. Like, what do we mean by GPT? What is ChatGPT? And there are lots and lots of LLMs, right? But all LLMs generally are built on top of the GPT architecture only. So we'll see how exactly each LLMs work. Like they nowadays they mimic human responses. They mimic human reactions. Like they can perform like humans. Ask them to write summaries, poems, and lots of creative tasks, and they're quite good at it. They are also good at it, assisting assistants, code assisting, and etc. So we'll see how what is the architecture behind the generation part. So okay. So this is our agenda for today. So we'll start with what is ChatGPT. Then we'll start from the very basics of how does a machine learn. And then we will go to how does that model output a word. Then from there we will catch on to transformers, which is the main architecture behind GPT. In the transformers, there is the attention mechanism. So we'll cover that in quite detail and like how it's implemented, how it's calculated, everything we'll cover. Then there is a beam search, which you will know why it's used there and then. Then we'll also cover the GPT overview, like how what modifications were made to the transformers model to reach to the GPT. And then we will again go a step further, like what modifications were made to the GPT architecture to go to the Chat GPT. Then we will cover Chat GPT limitations, and then we'll go FAQs. So FAQs will like I'll take all the questions during the webinar and will answer each of them. So at CloudX Lab, our vision is to upskill engineers and IT professionals in deep tech, deep learning, machine learning, and big data technology. Like in the phase of generative AI, I think even if you are an AI engineer or not, everyone should know AI. At least everyone should know how to use AI. For that, it's very essential to know like how AI actually works, because then on like when you understand the architecture behind it, then only you can make the best use of it, bring the best out of an AI tool. You may see like some people are able to get a lot from the AI and some people are not. So the only difference is that they understand the architecture, and that's how they can command the LLM better. So that is our goal at Cloud Accept, to upskill engineers and IT professionals. We generally prefer a hands-on way. I'll not go much into the deep introduction of Cloud Lab because that's not the goal here. But yeah, so you can check out our websites for website, which is at cloudxlab.com, to check out our courses and to be stay tuned in the new technologies such as generative AI, artificial intelligence, building from the very basics of machine learning. So yeah. So here we have ChatGPT architecture with explain. So okay. Now what is ChatGPT? So most of you would have used ChatGPT by now, if I am not wrong. So I guess everyone is familiar with ChatGPT. So again, to remind everyone, feel free to ask any doubt which you think. And no doubt is less, and no doubt is more. So yeah. So ChatGPT is an AI model designed to understand and respond to human language naturally. It falls under the category of natural language processing, or NLP, which simply means teaching computers to understand and generate human language. You have probably like interacted with some basic chatbots before ChatGPT. Like think now before 2022 era, like there were chatbots for each site, which can do basic of works. So like the ones on websites that give automated responses. But like ChatGPT is different. It doesn't just pick from pre-written answer. Instead, it generates responses on the spot, making it feel much more natural and almost like talking to a real person. Like I've actually tried a lot of different queries, which I like to show you how it exactly works. So here's the first one. Like I have asked it to write a marketing strategy for a new startup that sells legal software to help manage contracts and so on. I gave a detailed prompt like what exactly and why. And what you get back feels as if a highly experienced marketing expert put it together. Like it's a very detailed report on what we need to do. And this is a very basic version of ChatGPT. Nowadays, like there are lots and lots of better models which can give you analysis part by part or topic by topic. So, which can even analyze the situation, analyze your requirements, and give the response accordingly. So it's getting more advanced now. You can also write a description for a webinar on ChatGPT architecture. You can ask it that, and like it actually generates a structured, well-organized response in seconds. It like broke down what we need to what this webinar is about before without even providing a input about what we will actually cover. So that's something uh, good. Or if you're a programmer, you can ask for pseudocode to invert a binary tree and it will generate the logic for you. Beyond these examples, ChatGPT is a powerful tool. Like it can generate and refine content, summarize long document, and assist with editing, grammar, and rewriting. It helps with research, answering questions, explaining concepts, and simplifying complex topics. Businesses use it for customer support, like nowadays. They also use it for email drafting, report generation. While on the other hand, if we if we see from the developer's purpose, they use it for code assistance, debugging, and documentation. It's also great for creative writing, brainstorming ideas, and language translations. All these capabilities are powered by the GPT architecture, which we'll now explore. But I'm going to like walk you through what makes ChatGPT so powerful, like what's the science behind it. Let's start with very simple example. Like this is the first point when we go to understanding machine learning. How does a machine actually learn? A machine doesn't learn the way humans do. It doesn't have curiosity, intuition, or experiences. Instead, it learns by examples. Instead of programming a machine with a strict rules like if X happens, do Y, we show it data. We say this is good and this is bad, and let the machine figure out pattern. Think about like email spam detection. One way is to hard code rules. Like if an email contains free money, mark it as spam. But that's limiting. The better way is to convert emails into numbers and feed them into a machine learning model. We label some as spam and some as not spam and let the model figure out its own rules. That's the heart of machine learning, finding logic from data instead of us explicitly writing the logic. Now, a very popular technique for making machines learn is called a neural network. It's like inspired by the human brain. Neural network are a simplified version of how real brains work. Uh, think of it like a giant grid of knobs. You feed input on one side and the output comes on the other. But how do these knobs get fine tuned? Like, are these some random tune knobs and it's working? No. So that's what like training our machine learning model is all about. So during training, like we give inputs and expected outputs. Like suppose if we consider for cat, suppose we are training a neural network which can classify whether a image is for a cat or not. So we'll show it a thousand of images of cat and show it thousand of images of the animals which are not cat or the images which do not contain cat. And we will tell it that this one is of cat and this one is not of cat initially. And again like we'll give this information. Now we will ask it to predict the value for our image. So we'll give it an image and we'll ask it to predict whether the image contains a cat or not. Initially the model might guess wrong, but we adjust the knobs to get closer to the right answer. Over time the model improves. This tuning process is called backpropagation, like where the model learns from mistakes and tweaks itself to make better predictions. Now in GPT models, we don't have just a few knobs. Like we have billions. Like GPT-3 had 175 billion knobs or parameters that needed to be adjusted. So if you think about taking each knob manually, it's impossible. That's why we use a smart approach. Like instead of randomly adjusting everything, we make small tweaks. Check if things improve and adjust further. Just like you slowly adjust a water tap to find the perfect temperature. In the similar way, we tune the like when we tune the geyser, oh it becomes too cold. Oh no, it's too cold, and then a specific point come. Oh now this is the water which I need. In the similar way, we tune the noobs for the neural network, but not manually. There's a algorithm behind it, and yeah. But yeah, overview is something like this only. So once like training is done, the model freezes these no positions. Like when you ask ChatGPT a question, it doesn't learn on the spot. It just look at the frozen model and gives you an answer based on what it learned earlier. That's called inference, like using a trained model to generate predictions. So, in the same way, like we set a gauger position that now this is the temperature which I want, and now every day you can use the same knob. So, in the similar way. So, like if you see it on the screen, each knob is to a different number. So, this is what contains of the training process of the neural network. So this was a like little overview. Now let's jump into brief maths. Like I'll not go much into details about maths, but let's understand what is exactly happening. So like at its core, neural networks are made up of interconnected neurons, like which are mathematical nodes organized into layers. Think of them as a web of adjustable nodes. So like here we have input layer that takes raw data, like whatever data we have, we pass it to the input layer. Then there are hidden layers which process patterns and learn from data. Like there can be any number of hidden layers. The more complex the problem is, more number of hidden layers we generally require. Then there is the output layer, which gives us the final result. So, like input layer takes the input, hidden layer does some work and analyze the pattern on the data, and then it will make and then it passes the information to the output layer. And based on the received information, output layer uh, like uh, predicts a value, and we also have the actual value of that input. Like suppose if we input image of a cat, we know that it is a cat. So in case a model tells that it is not a cat, like it predicts wrong value, so we calculate the error between the predicted value and the actual value, and then we update the okay, I guess I'm not in like we tweak the knobs based on the error value. So okay, now this is not correct. Okay, now let's tweak it again. Then we pass another image and we see okay, now for this it predicted correct. Then let's leave the knob as it is. Now we'll pass it the next image, and for next image, like if it again like predicts incorrect value, then again we'll update it. Okay, this one is again not working. So let's tweak the knobs a little. So, like by adjusting the connection between these nodes, the network learns to recognize patterns and make predictions, just like how our brain processes information. Mathematically, the equation governing a neural network is just y equal w dot x. So, like the dot product of weight matrix and the input. So, x is the input, like the data which you provide to the model, and w is the weights. So, like this weight matrix is exactly what the model learns over time. Like it is a matrix of a particular shape. Like the shape we decide based on what we want for the output, and based on the input shape, like what shape is input for, and why the predicted value. So the weight matrix is crucial because it stores the learned information. It is an M into N matrix generally, where each value in the matrix this represents a knob that controls how much influence a particular input has on the output. So like each value denotes how much influence this input will have on the output. So that's the whole part about the weight matrix. Now, how does learning happen? Initially, the weight matrix is either set to random values or to zero. Think of this as setting or like settling all the knobs to random positions or turning them all off. So you could choose anything. Now, given an input x, the model calculates an output y using the equation y equal w dot x. So it takes the dot product of w and x and predicts the value y. So since the weights are random at the start, the initial predictions are usually incorrect. The model compares its predicted output with the actual output, like the ground truth and the predicted value. The difference between them is called the error or loss. And to minimize this error, the model adjusts the weights. So the weight values are tweaked slightly in the direction that reduces the error. The goal is for the predicted values to get closer and closer to the actual values. We keep on updating the weight values to reduce the error. So that's the whole goal of training. Like just keep on updating the weights value until we reach the optimal value, like in which the error is minimum. Yeah, like eventually the weights settle at optimal values, allowing the model to make accurate predictions. And then we use the learned weight matrix in real world to predict the output for an input X. So this is how exactly the neural network works. We have our weight matrix, we have input, and then we just keep on updating the weight matrix until the error for the whole data set is minimized. Like if we have 10 instances in our data set, so we will reach out to the weight value considering all the 10 inputs on our data set. So is everything clear till now? Let me open the YouTube chat also if there are any questions there. Okay, so I think everything is clear till now. That's good. Okay, so this was a generally a little mathematical die, but I think like it's pretty clear to every one of you. Now, like we know that it's no magic, it's just some W into X happening here, W dot the X happening here. So we'll jump into our next step. Now we know like how neural network works. Let's like ask a fundamental question, like how does the model generate a word? At first glance, this seems like a tricky problem. Like after all, language is complex, and words are not just random sequences of letters. They follow patterns. But from a machine's perspective, predicting a word is simply a classification problem. Like the classification problem which we just consider, whether to classify whether a image is of cat or not. This is a simple classification problem. And this is the architecture which it actually uses to choose the word. So what does it mean? Now let's see. Well, imagine the model has a dictionary of 50,000 words, like every word it has ever learned. Like for us, the dictionary is too wide. But suppose we first give machines only 50,000 words, and for the model, only these words exist. Okay. So we represent this dictionary in a structured way where each word is assigned a unique numerical index. Like here, the is assigned one, and is assigned two, dog is assigned three, and a similar way. Now, when the model needs to generate, yeah. Now, when the model needs to generate the next word in a sentence, it doesn't just magically come up with it. Like instead, it does something really interesting. Uh, yeah. So it calculates the probability of every single word in that dictionary being the next word. Yes, or like all 50,000 words. It may seem confusing now, but let's understand how it exactly does that. So suppose like we have this task, like we have the task to predict the next word in a sentence, and the input is the cat and the dog. So we have to predict what word will come after this. Now we know that machines don't understand language like we do. So at first, like convert it converts each word into a token using its lookup dictionary. So it will map each word to its index. So based on the dictionary, if we go, the will be represented by one. Cat, if we go, so cat is here at fifth position, so which you can see here. Cat is at fifth position, and then if we go and is at second position, and the is again at the first position, and dog is again at the third position. So here is dog. So this is how we represent it. Now the model takes these tokens as input and generates a probability score for each word in its dictionary, like all 50,000 words. So it generated like, okay, for token one, which is the. So the cat and the dog, the. If the is the next word, the probability is only 0.001. So here we can see that. And for like second token, which is n, so the word a sentence with the cat and the dog, and this is the probability is also very less. So the highest probability which we can see here is of fourth token, 0.85, which is when we look into a lookup dictionary, it's play. So the cat and the dog play. So this so we do a lookup into a dictionary and we find and choose the word play here. So the most probable word is generally chosen as the next word. So this is the process how neural networks actually output a word, and this same process happens in ChatGPT or any other language model. Like when you type a question, it predicts each next word one by one until it constructs a response that makes sense. So yeah. So I saw a question. So I'll probably take it. How generating words become a classification problem? So we know, as now we show, like in this case, we have 50,000 classes because there are 50,000 words. So output can be only a one word, right? So it's generally like classifying based on the classifying on a data set of 50,000 words. So that's how it is a classification problem. In the classification also, it generally assigns probability to each input, and the most probable input is generally chosen, and which follows similar thing on output purpose. So is it clear, I guess? So yeah. If you have any more questions, ask. Feel free to ask. Yeah. There could be so Veena has asked that there could be multiple words with same probability. Then how will it select next word? Veena, like it's not generally that there are multiple words with the same probability. And to answer you, in the agenda, I told you that we will be discussing beam sets. So this is the algorithm which we take to generally handle such cases. So we'll cover this in later in the lecture. Okay, so now we know how neural networks actually output our. So we can jump into the transformer architecture. So like transformer was a very big breakthrough in the field of natural language processing. Natural language processing is just an AI field that deals with text. So like researchers at Google introduced transformers in 2017 with a game-changing paper called "Attention is all you need." Like if you can look to the paper, you can search "Attention is all you need" and you can see the paper. So at the heart of the transformer, there is something called self-attention. Like this is what makes it powerful. So like first of all, the transformer is designed to process sequential data such as text or time series data. So now how does the self-attention actually work? So like imagine you are reading a sentence like the cat sat on the mat, like because it was tired. So the sentence is the cat sat on the mat because it was tired. So as humans, when we see the word it, like because it was tired. So in this, when we see it, we instantly understand that it refers to the cat. But neural networks had trouble making these connections. Self-attention like fixes this by allowing the model to focus on important word in a sentence, no matter wherever they appear. So every word doesn't just look at the next word, it looks at every other word in the sentence and assigns important scores to determine which words like matter the most. So it may seem a little confusing again. So again, we'll choose the way of maths to understand these concepts. I don't know why, but my uh, okay, okay, Disha, like you can rejoin the call, and I guess screen will be visible to you. So yeah, but my like okay, we have one more question. Let me see. Yeah. Okay. So feel free to like ask the questions, and I like now I'm assuming that up to how model generates a word, everything is clear to you. So if you like everything is clear, then also you can like comment and see. Now let's go to the next slide. How self attention actually works. So suppose like we have a input sequence as I love transformer. Each word here is like first converted into a vector representation using word embeddings. So this helps the model understand. Uh, sorry. Yeah. So each word here is like first converted like to a embedding. So this helps the model understand like words in terms of numerical values. Like as we have already seen that machines do not understand anything. So suppose like I embedding for I is represented by a vector of shape 1 by 4. Like one is the row here. and 4 is the columns. Like now each each word will be represented with the embedding of same shape. Like love will be also of shape 1 by 4, and transformer will be also of shape 1 by 4. Now, so yeah, yeah. So now, now we have computed the embeddings for each of the words. Now each embedding is transformed into two different vectors. Like first is the query vector. So query is a like representation of the word used to derive attention scores, like for other words. The query vector represents the word or token for which we are calculating attention weights concerning other words or tokens in the sequence. For example, if we are considering the word love, the query might be what other words help me understand the meaning of love in this sentence. And this is also not only single words, like how all other words contribute to me to understand the meaning of love. So this is generally how what the query represents. Like what other words help me understand the meaning of love in this sentence. Then there is a key vector. So like key is another representation of the word used to compare with other words. So like it is used to compare with query vectors during the calculation of attention weights. The key acts like an answer to the query. It tells us how relevant each other word in the sentence is to understand love. So it's like a vice versa of query. Query told us like what other words help me understand the meaning of love, while on the other hand, key tells us how relevant each other word in the sentence is to understand love. So these are the two vectors which we calculate after like till now we have done two steps. So like first we have like we received an input. We first converted each word in that into an embedding. To embedding is generally a machine representing format of a thing. When we understand something, we have understanding it in our brain. We cannot explain it like how exactly it is in our brain. So we use language to communicate our thoughts to other person. In the similar way, embeddings are just the thoughts. It captures the meaning of that word in the machine learning or machine format. How it is actually calculated. So like key and query vectors are obtained by multiplying the input embeddings with the learned weight matrix WQ and WK. So WQ and WK are the weight matrices. Like we saw weight matrices when we were learning neural network. So in the similar way, here we have two weight matrices. One is WQ, another is WK. Now let's consider only WK. So like as here we calculated query vector for word I. So like QI is representing query vector of word I. So we take dot product of like embedding vector. So this blue is the embedding vector, and we take the dot product of it with the WQ. So it like when we take it, we repeat this for it will give us the value which is these three. So how us like when we multiply two vectors or matrices, so it needs to be like m into n should be into n into p. Not to I don't want to jump into mathematical terms, but this is the basic rule to multiply vectors. That if a first vector is of shape m into n, then the second vector first shape should be n. Like the number of columns in the first vector should be equal to the number of rows in the second vector. So here we have four columns. The shape of Q embedding vector is 1 by 4. So the one is the row, and there are four columns here. So in the second vector, there should be four rows to make the computation possible. So here we take the example 4 by 3. So the final query vector comes on the shape of 1 by 3. So it's like it becomes m into p. So it will like the first dimension will be of the first vector. How many rows are in the first vector, and second will be how many columns are in the second vector. So there are one row in the first vector. So the number of rows in the output is one, and that there are three columns in the second matrix or vector. So the number of columns in the output is three. So yeah, I think I made it a little complex, but this is generally how it works. So like Qi is equal Qi is the embedding vector and dot WQ, which it gives us the so this light blue or sky blue vector represents the query term for I. Uh, we do the similar thing for J vector. So yeah, okay, it's not working. Give me a minute. Yeah. So in the similar way, like we calculate key vector for each word by taking the dot product of embedding vector with weight matrix WK. So we have to initialize two weight matrices till now, WQ and WK, and both these weights are learned during the training. So this is the whole goal of us. Now let's understand it in more clear way. So this is generally the self attention mechanism. So till now we have calculated in if we see here I have only shown Q and I K calculation for the word I, but we represent the similar computations for each of the word. Like for love we will again calculate. So we will pick up the embedding for love, and again we will take the dot product of it with the WQ and WK vectors to get us query and keys. So for again here also we'll take the embeddings of all the words and multiply it with WK vector to give us the key vectors. So after this, after we have computed the key and query vectors of all the words, we calculate the attention score. And attention score is like to determine like how much attention a word should pay to another. We compute this score by taking the dot product of the query of one word with the key of another word. Like this tells us how relevant they are to each other. So like in this, if we see, so this is attention of I and love. So here we take the query of ith vector and we take the dot product of it with love word, the key value of love vector, and whatever the score it gives us, it will like here it will give only a one shape. So we like this like this attention score whatever I don't know the color like grayish blue color the block which is here. So whatever it is, it represents like how much attention, how what is the relevance between the word I and love. So this is what we have calculated here, and yeah. So the attention score of the word I will be a vector of three individuals score. Like each score like represents the attention. Each score like represents the attention I gives to itself, love, and transformer. That's why there are three words. Based like this all is based on the input which we expected. That the input which we expected is the sentence I love transformer. So that's why it will like only contain for three individual scores. If there were n number of words, so the attention score of I would have been calculated with respect to each word. Like attention I love, then attention I transformer, then attention I where, whatever words will be there. So for each word, we would have computed the attention score for I. So higher scores mean like more focus on what that word, while lower score means less focus. So here, like if you see the third, the three, it gives us a vector of shape three, a list of three elements. So first word is Qi into Ki, which is the relevance of the word with itself. Then the I with love, and then the I with transformer. So this, so that attention score of the I word or the first word will be a list of three attention scores. That is the with I, with love, and with transformer. So in case there are n words in our input, so the attention score of a particular word will be a list of n elements. So I think that it's clear to you. Okay, we have a question, I see. Let me see. What is WK? WK is the weight matrix. Like it is not the query vector, The weight matrix is the one which we learned during the training. Like in a neural network, we initialized weight matrix to a zero or random value, and then we tuned its values based on the what results it gets to minimize the error. We follow the similar pattern here also. So yeah. So now that we have, okay, again to revisit, first we computed the embeddings for each of the words. Then we computed query and key vectors based on the WQ and WK metrics for each word. Uh, then we computed the attention score. So like here I have only computed for attention I. In the similar way, we'll compute attention for each of the words. So for love, it will be attention love I, attention love love, and attention love transformer. So again, it will be a shape of three, where first will represent attention of love with I, then how much attention uh, love should give to I, how much attention love should give to love, how much attention love should give to transformer. So this is what each score will represent. Again, higher score means more focus on that word, while lower score means less focus. So now that we have calculated the attention scores, we notice that these scores can widely vary in magnitude. Like some values may be much higher than others, while some may be very small. However, these raw scores alone do not provide a clear interpretation of how important each word is relative to the others in the sequence. To address this, we convert these scores into probabilities, ensuring that all values fall within a meaningful range and sum to 1. What benefits here is this allows the model to weigh the importance of each word more effectively, while like maintaining the original scores. So mm, to sum up, okay, let me show you. So how do we achieve how do we achieve it? We achieve this by like using the softmax function, which not only normalizes the scores but also amplifies the higher values while diminishing the lower ones. Let's see what I'm telling. So if you see here the graph, so in the index bar plot of the original array, you can see that zero index has one value, one first index has two value, and so on, three, four, five, six. So these have these values. Now apply softmax function on that, and we convert it into a probability. So like as we know that highest value was of fifth index here, uh, highest. So again, it will again take a higher probability. So we can see here that 5 has the highest probability, which is above zero point 0.6. Then there is 4, which is above zero point 0.2, and so on. Like all these value, when you'll sum them, they will sum up to 1. The most interesting part was that there was not much difference in 5 and 6 value in the original graph, but still, when we see it in the probability, there is a lot of difference. And that's why we generally do not use the normal probability computation. We instead rely on shorthand, because this is what we want. We want to diminish the chances of the words which are not to be the next word in the sequence, and we want to maximize the probability of the words which have the probability of being the next word in the sequence. So that's why we use the short. So now you have clear idea of why we like here we have a little idea, okay, so that's fifth word is has more important than the fourth word, because it has more value than fourth word. But probability gives us the exact idea of what exactly is happening, and exact range, and the difference, everything. So that's why we use the softmax here. How it exactly works. So for the input, like I love transformer. Suppose the raw attention scores are like I 2.7, love 5.1, and transformer 3.2. So like these values don't clearly like indicate relative importance. So like after normalization, when we do normalization here, they might become like one I equals 0.2, love is 0.5, and transformer is 0.3. So when we sum again, the sum is 1, 0.5 plus 0.3 plus 0.2, that is 1. This way, the model understands that I gets the most focus on love, than to compare to the word transformer, because the love score is zero point 0.5, and this all we have done for attention of word I. So the maximum score is for love, so we tell that most focus should be on love, but it does not tell that only focus on the word love. It also tells that you need to focus by a magnitude of zero point 0.5 to love, and a zero point 0.3 to transformer. That means like slightly less you can focus on transformer, and the most less you can focus on yourself. That also makes sense, because uh, you will not get much input on referring to yourself. So it only not like tells that this is the most relevant word. It just gives you the probability distribution of each word, and so it can rank each word based on its importance, and can like extract relevant information for each word from each word. So this is what we do here. But one problem when we practically implement it, the comes in dot products like grow large in magnitude, where the application of the softmax function would then return extremely small gradient. We have already seen that in the previous graph, there were only very few differences. Still, like in the softmax probability distribution graph, there are huge differences between each value. And this is like when there is a constant scale, like there is only difference of one between each input value, which you can see here. But when we compute dot product, there can be any value. Like you can see here, it's 2.7, then 5.1, then 3.1. It can have any range. It can have any value. So, the problem becomes that when we apply softmax to such unscaled data, it return extremely small gradients. So for that, we first scale the scores before passing it to the softmax. So this is just a prior step to applying the softmax. We first scale the attention scores which we receive to a particular scale, and then we pass it to the softmax so that the gradients are stabilized, so that our learning just does not get stuck like this and this. So yeah, I'm hoping that everyone is clear on what I'm telling, and I'm not just going ahead splittering my knowledge. Uh, feel free to comment that if you are understand, if you are able to understand, so I'll know that yeah, you are getting it. Otherwise, I'll change. I can like explain in more detail. So yeah. Now we are like just one step away from getting our final attention scores. Like so far, we have determined how much focus each word should receive, like using query and key vector. However, we still need to determine like what information each word should contribute to the final output. For this, we use value embeddings. Previously we had two weight metrics, WQ and WK. Now we will have three weight metrics like WK and WQ and WK, which we used before. Now we introduce a new weight matrix, that's a WV, which help us to calculate the value embeddings. What does value embeddings represent? That what information each word should contribute to the final output. This is the one use case of value embedding. Second output use case is uh, for what dimension we want the attention scores to be presented. What is the shape? What should be the shape of the output? Whether the vector should be 1/4, 1/5, 1/6, any like previous attention scores previously are of the space or of the shape 1 by n, right? Like where each value represents the attention which that particular word give to the nth word. So now we do vocabulary can be too long. There can be 1 lakh words, 10 crores work, 10 crore words. It can be too large. So we cannot like pass on the attention scores of a shape like 1 is to 10,000 or 1 is to 1,000,000. We cannot pass. So that is also one reason we use the value embeddings here. We decide the shape of WV vector based on how we want the output to be. So value embedding decide what actual content should be passed forward after applying attention. So just like we did for query Q and key K, we calculate the value embedding as score dot WV. Here score represents the attention scores and WV the weight metrics learned during training. So like here we are calculating the value matrix of I. So it is of shape 1 by 3. So now here we have now we want it to remain of the shape 1 by 3. So we chose the shape of it to be 3 by 3. Otherwise, like suppose we want it to project into we want the output of this output of the value embeddings to be a shape of 1 by 10 suppose. So what would we have done there? We would have keeping WV of shape 3 by 10, and in the output, like when we will do score I into WB for a vertex 1 by 3 into 3 by 10, so 3 will get cancelled and the output will be of 1 by 10, shape of will be of shape 1 by 10. So yeah. So in the same way, like we calculate context vector of all the words in the sequence. So this is like self-attention mechanism. To sum up, like we first calculate embeddings, then we calculate the attention scores using query and key vectors. Then we convert those scores to probabilities, and at last we convert them to the context vector using value weight matrix. By dynamically adjusting focus based on the context, self-attention helps transformers understand and generate language with remarkable accuracy. So now we jump further. If there are any questions, you all guys can ask. Yeah. So again, I think everything is clear, the competition part and everything which is there. Uh, like how the shapes get projected. Anyway, the shape is not the key part here. That's just a maths. But how the values are actually converted, like how we take, how we perform the competition. So is everything clear to everyone? Do you have any doubts, or we should proceed further? We have a doubt. So how do we calculate value embeddings? Okay, Veena. So like, okay, that's a good question. So like we computed scores in the previous step. If you see here, so this is we calculated the attention scores here. So this blue represent the attention I. So we just use this score and we take a dot product of this score with the matrix WV, and the WV is the weight matrix which we like at first initialize using a random value, or we keep all the value zero, and then we like tune the weights during the training process until we reach like for the transformer model there are three matrices which it needs to learn during the training process. One is the WQ, one is WK, and one is WV. So when we train the transformer architecture, we just keep on tweaking the weights on all these three metrics until it reaches a optimal state. So I hope it's clear to you. Anyone, any more questions? Next, we will like jump on to the like we have covered the self-attention mechanism. So we'll jump onto the transformer architecture. Okay, I guess I can jump further. Okay. So now we know self-attention, but to understand the concept of transformer, we need to understand two more concepts. First is the multi-head attention, and second is the positional embeddings. So instead of using like just one attention mechanism, we split the input into multiple smaller parts called as heads, and we apply attention to each separately. Now the question arises, why do we do that? We do that so that each head focuses on different aspects of meaning, and such as like grammar, context. We know that a word can represent multiple context, right? Uh, even if we suppose we say only a word "oh," so we can say it in multiple ways. Like we can be shocked and say "oh," or we can be surprised and say "oh," or when we understand something, so we say "oh." So in the similar way, each input can have multiple context. So by passing the input to different attention heads at the same time, we just expect that each head captures a different aspect of the meaning of the context. How do we ensure that? Because like each head is like okay, one head like the self attention mechanism which we just learned. Understand that it is replicated in one head. Now, same mechanism is again replicated in another head. The difference will be the weight matrices will be differently initialized in another head. They were on the first. So, basis on that, the same input will lead to different outputs. So most probably it will like learn different thing. So like after computing attention for all heads, like there are suppose there are n heads, so we will like initialize NWK matrix, NWQ matrix, and NW V matrix. As each matrix will be initialized differently. So during the training also it will like have little different value, and that makes it possible to interpret different context. So after computing attention for all heads, we combine their results to get a richer understanding of the input. So this helps the model capture complex relationships better than a single attention layer. So this could have been possible for from a single attention layer also, but to increase the accuracy, to increase the context what a model can understand, we just introduce multiple heads. So so that it individual computations go on inside each head, and then at end we sum up all those learnings, and we prepare a representation of attention. So this is one concept for multi-head attention. Second concept comes as positional embeddings. So like since a transformer, okay, like so what happens is transformers process each word at once. They do not process words in a sequence. Like suppose we have I love transformer, so it will not happen that we first pass I word, then we pass love word, then we pass transformer word. Instead, we pass whole sequence at once. So what happens is that when we that transformer generally parallelizes everything and then the competition. So during parallelization, what generally happens, the position of the words is lost. The information about the position is lost. So to solve that problem, we add positional embeddings to give them a sense of sequence. Like how we assign each position a unique encoding and add it to the word embeddings. So the embedding which we calculate, in that only we encode the positional encoding. So like this help the model understand word order, like knowing that I love transformers is different from transformers love I. So these two are different sentences. So that we are encoding the position, the sense of position of that sequence in the model. Now that we have covered self-attention, multi-head attention, and positional embedding, let's walk through the overall transformer pipeline. Okay, now this diagram may seem a little scary at start, but let's see what it exactly means. So let me use an annotation here. So first we have inputs here, which you can see. Then we use the embeddings layer to convert it into embedding. So then it is converted to embedding. And here the positional encoding is stored for each word. So we take the input embedding from here, and we then sum up it with the positional encoding to include the information of positions in the embedding itself. So that's why we concatenate here, which we can see the plus sign here. So this is the first part before passing it to the encoder. Now we have you can see that first of that encoder it has both encoder, it has encoder and decoder block. So again, this block is called the encoder block, and this should I change the color, or let me just use the same color? I'm not quite good with drawing, but yeah. But it's good enough to explain things. So this one is the encoder block, and this one is the decoder block. So the like the task of the encoder block is to encode the embeddings into a representation that machines can understand, and then we use the decoder block to decode the learnings which we learn. So let's see how exactly we do that. So, after generating the embeddings and infusing the positional encodings in that, the embeddings are passed to the encoder block. The encoder consists of multiple identical layers, each containing like each word attached to every other word in the sequence itself using self attention. Multi-head attention like allow the model to learn different types of relationships in parallel. So that's the whole idea of behind multi-head attention. So like here there are so many heads of attention going, so there are so many competitions of attention going on the input embedding which we pass. So this is one thing. So after the multi-head attention returns the attention score, the scores goes through a fully connected feed-forwarded network layer. So it helps the model to capture complex transformations uh, 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 layer. We generally include so many blocks here also after the multi-head attention. So what exactly it captures is complex transformation, and in this only there is also a layer normalization happening. So layer normalization generally like normalizes the scores which after the feed forward layer just to stable the learning. So the encoder processes the entire input sequence in parallel and produces context context rich representations. And like here we can see that there are several n number of encoder stacks. So these all encoder stacks are encoder blocks are stacked on top of each other. So the input from this block, like after let me see, after it is passed to the feed forward and add and norm layer, again it will be passed to another encoder layer only. So we generally repeat this process n times. So yeah. So and denotes the number of encoder which we have. So we repeat this process n times, and then we jump into the decoder part. So like several such the information like flows sequentially through each encoder block. So uh, okay. So this continues like block by block, refining the learned representation. So each learning is defined by each encoder stack again and again. So the final encoder block outputs a context-rich representation of the entire sequence, which is then passed to the decoder. Decoder again consists of multiple layers similar to encoder block, but with an additional mechanism that is called masked self-attention, which you can see here. Now, this may be confusing at the start, but let's understand what it is. So, masked attention is nothing like again different from self attention. Okay, since the decoder generates the text step by step, it should not cheat by looking ahead at future words. Like because during training, we during training entire sequences are passed to the model, and that means it has the decoder has access to all the previous words and also all the future words. Our task here is to predict the next word, but during the training it already has the access to the new word. So we generally mask those words to prevent that decoder do not see them during training. So, to prevent this, a mask is applied to the self attention mechanism, ensuring that at each step, a word can only attend to previous words in the sequence. So, it cannot calculate the attention scores for the words which are yet to be predicted or which are yet in the sequence. So, this is what a masked multi-head attention does. The final, then there is the again we there are and decoder blocks. Following the similar pattern, there are multi-head attention blocks. Then there is a feed forward layer and everything. Then we pass it to a linear layer, and again we pass it to a softmax layer with outputs a probabilities. So the final layer produces the probability distribution over vocabulary words, which we show. So for each word in the vocabulary, it will assign a probability. which helping the model like generate fluent and meaningful text. So the process repeats until the full output is generated. So this is what actually happens in here. So it may be again little be confusing. So let me even make it easier for you. Let's take an example. Let's say we want to translate "I love transformers" into French. So how does this transformer? How will the transformer handle it? So first we take our sentence "I love transformers" and convert each word into an embedding from the embedding layer. And now like then we will like enrich it with the positional embedding. We'll concatenate it. Now this processed input goes into the encoder stack, which like gives such a rich context-aware representation for the sentence, ready for the translation. Now after after that information is passed to all the encoder blocks, but however how many are there in the stack? Then it passes the info here you can see to the decoder block. So now let's move through the decoder. So in decoder here's something happened interesting. Like unlike the encoder, the decoder doesn't see the whole French translation at once. Like it start with just the first word, say jam, and has to predict the next word step by step. So jam, I suppose represents I love. Uh, so so it like first starts with the first word jam and had to predict the next word step by step. So during training, the model is given the full correct output sentence jam, less, transformers. I'm not sure what the translation will be, but somehow that. So however, like when generating text, it must predict one word at a time without knowing the future words. When it is translating the second word, it should not priorly know what word is coming at the third number. If the model could see the entire sentence at once, it would be cheating. Learning patterns like it shouldn't rely on during real word. So that why we would mark the self attention here, so that only word jam is visible till now, and the decoder only knows the part of jam, and it now it can predict the next word, what will come next jam. So the marked attention blocks the model from looking ahead at future words. At at each step, the decoder can only use the words it has already generated, forcing it to learn how to predict naturally, just like in actual translation tasks. At the same time, the decoder is also attending to the encoder's output, pulling relevant context from the original English sentence to make accurate translation. So, like once the decoder processes the input, it predicts the next word, say less, and then the next one until we get the fully translated sentence like Jame less transformers, if that is the correct translation. And just like that, we have translated our sentence using a transformer. So if you see, okay, now one part interesting comes here. We see two connections here. One is this connection and one is this connection in the decoder block, right? So the input is flowing from two directions here. So what it generally means is, first of all, we pass the first in output token here during training we pass the first output taken. So suppose the first word for the French will be jam, Jaime. So what shifted right here means that we generally shifted this word to the first index. Computer terminology generally start with zero. So we shifted this to the first index, and at the zeroth index we use a token such as start. So that would denote that the translation has started to the transformer. So it can like start the verb. So we take the output, and then again we encode the output into the embeddings. Again we okay. So what output will be given here? It will be Jame. Okay, let me write it down here. Here it is. So, suppose it is Jame less transformer. So how what shifted right means, we'll add a token here, start, and generally we also add it in end. So this is what shifted right, because now the Jamie gets shifted to the second position. So This is what we mean. So again, we will encode this input into using the embedding layer, which is the output embedding. And then we will encode the positional encoding again. So here you can see, we'll again include the positional encoding. And then you can see that the information is first passed through the attention block. And again, it is like passed to the this masked multi-head attention. And what happens here is we generally pass this the embeddings of this what this start jam last transformer and to here masked multi-head attention. So at the time, like suppose we pass jam here and the task is to predict the less here. So we will like it will like that it will be passed like uh, start jam. Only these two words will be there, and other words will be represented as this start as a mask master. So it cannot like see these words. So for the decoder block, only these words exist. Jammy start. So this task is done in the masked multi-head attention, and then it is like passed to the normalized here. Now here it like takes the information from the encoder block, and this information with the attention score for the output which it has generated. So combining both this attention block, if you see, it takes. Let me clear it first. So this attention block, if you consider, so it takes input from the encoder block and one input from whatever what embeddings which we learned. So this generally like the input from encoder represents the contextual representing from of the English representation, and this attention generally represents the contextual representation of the French word. So it sums up both the information here in the multi-head attention and then passes it to the feed forward layer, and then again it can converts into shortcut. So this is the training process in the in the prediction or during the inference. We anyway don't have access to the next word, so it goes on the similar way. Now, based on the output probability, we again calculate the error and then we update the architecture weights according to that. So the weights will be WQ, WK, and WV in the both encoder and decoder block. So this is the whole architecture of transformer. I hope there are doubts now, because it's a complex topic. So let me whatever doubts you have, feel free to ask. Uh, so Prince, like there is no difference between embedding and encoding. Like those are the same term. These terms are used interchangeably in ML domain. So is the transformer architecture clear to you or not? Or will you like to do you have any questions before we jump into the beam search? Till then you ask questions. I'll sum up everything for you. So what happens? We pass the like suppose the trans for the translation work, we have I love transformer, and for that the French line translation is Jamal-S transformer. So we will encode both the sentences using the input embedding and output embedding. Then the input we pass to the encoder layer, and the output will be passed to the decoder layer. We mark the future token so it does not knows when predicting the next word. And then in this multi-head attention, we combine the encoder's representation of the sentence and the representation of the input which it see. The task here is to predict the next word in the sentence jame less transformer. So suppose it's passing jame, so it's tasked to predict less. So here, this representation of the decoder block represents what does the word jame means or what does the input sequence means. So that it in this multi-head attention, it generally compares both the encoder's value representation and the decoder's till now what it has learned through the output, and then it combines to predict the next word. Like based on that only, like okay, these words I have translated till now in the decoder. So how many, like what are the words which I have translated till now in the decoder? So generally this info is captured by this marked multi-head attention, and then coder gives it the whole representation of the whole word, and the decoder gives it the representation of, like to summarize it in easy term, encoder tells it that this is the whole task you need to do, and decoder marked multi-head attention here tells it that okay, this is the work done till now. Now see the encoder's work and see what else we need to do, and then choose the next action. So it then combines both the information and passes it to the feed forward neural network. Feed forward neural network is just a simple neural network which just combines all the information, and then it passed to the softmax layer, and it's passed to the output probability. And based suppose it gave another word, like suppose instead of last, second word should be less, les, it should be less, but instead it gave another word a high priority, then we will tell the model, oh, it should not give this word this probability, it should be less. So we will update the calculate the error value of each probability, and then we will update the weights. So again, okay, we have question here. Embedding of English and French I are those similar? Embedding of English and French. No, these are no, not similar. That's why there are two embeddings. One is the input embedding and one is the output embedding. So both are different. Any more questions before we proceed further? Okay, it's good that you guys are understanding everything, but that just puts me in doubt that you guys are like actually understanding everything. Uh, okay. What is add and norm layers to? What is the work of attention layer, and what is the difference between multi-head and masked multi-head? Okay, Prince, I'll explain this again. Add and norm layer is just a normalization layer. So here we just do the layer normalization, which is essential for stabilizing the values. Otherwise, like gradients can go to any value, and that can destabilize our whole training process. So to stabilize the training and see that everything goes smooth, we normalize the outputs at each layer. So the next layer receives a good sense of output, and those are not such random values. What is the work of attention layer, and what is the work of attention layer? So as we explained the self attention mechanism, the attention tells us that suppose there is a input that the cat sat on the mat because it was tired. So here, because in because it was tired, it represents cat, that we know, but how we will tell machine? So that's what attention does. For word it, in this case forward it will the model will like compute attention scores with each other word, and in that way it will learn representation of, okay, now it represents cat. So in this way, using the attention mechanism, the model generally learns what the weight means. What is the difference between multi-head and masked multi-head? In the multi-head attention, we do not mask any future words. In the masked multi-head attention, we generally mask the future words. So what does that mean? That in the encoder block, we are anyway passing the input task. But in the decoder block, we are passing the output. And the whole goal of the transformer is to predict the next word. So like suppose again I'll take my the translation example. So suppose the input is I love transformers, and the task is to translate into French. So suppose in the output I give first word as jame. It represents I guess it represents love. Jame represents love. So I give it that. Now, when I'll pass the entire sequence into this decoder block here, if you see, let me annotate here. When I pass whole thing here, So it will have also have access to next word, because the whole translation is Jame last transformer, and I it will have access to last transformer also. So that will make the translation bias, because suppose I give you the task that translate this word, translate I love transformers to French. You will also like begin with one word by one. But suppose I only give you entire sequence that the output is Jame last transformer. So in that case, your learning will be biased, because you will already know the output. So that will be kind of cheating, right? Because we already know the answer, so we cannot reach to the optimal value. So that's why we just mask the last transfer, the next words which are not yet predicted, which the model is yet to predict, so that model cannot see those words during training, and it cannot cheat, and it can learn the natural meaning of each word. So this is what generally happens. I hope this is clear now. Veena, why there is a linear layer before softmax? Just to bring everything in the linear format, because we know that softmax expects a vector. So, it expects the input in the shape of one. Okay, up to here, up to add and okay. Let me again annotate. Up to here, the shape can be any. The shape can be any shape. Like it can be m into n, one into n, anything it can be. But we need to output probabilities, right? And for each word, probabilities of each word will be a shape of 1 by n vector only, which we saw in how model outputs a word. That it's an output of 1 by n. The list is output of 1 by n, where each word, each index, each value represents a probability of that word being the next. So that's what the linear layer is for, to transform the input sequence into a shape of 1 by n vector. So I hope it's clear. So yeah. Yeah, it's flattening. Yeah, yeah, you got it, Venom. Yeah, we do flattening there. Okay, any more doubts? Those were really good questions, and makes me a little more confident that yeah, I am on the right space. Okay, any more questions before we proceed further? Anyway, like we can take the questions any time in the lecture. So I'll go now. Now, Vina, what you asked previously, that how exactly it what happens when two words have same probability. So generally, like it does not happen. Like anyway, it does not happen. There will be a difference even at the 10th decimal place, but there will be a difference. But that question raises a doubt, like how exactly it works. Like suppose we give chat gpt a input, like let me try. Hmm, I'm not sure if it works. Like, oh yeah, I am. Let's see what it outputs. I am teaching the transformer their secret control of layers and the attention control. Nice work, nice work. Now, again, I'll do that. See, it outputted, I'm giving the same input both times. But here it outputted, I am teaching transformers their secret control. And here it's just different. I am teaching transformer to listen, to learn, to see. Everything is different. But if we are giving it a same if we are giving it a same input, uh, if we are giving it a same set of input, so the probability of words will be same, right? The next word which comes after it, it will be same. So how does the chat gpt actually answers different versions based on the same input, expecting the same input? So that's where beam search comes in. So suppose we are building a translation model here. So comment Vastu Joel. So this is the French, and when we translate it into English, it will be how will you play? Uh, yeah. So okay, we change the input here. So it's comment vastu, and now it can like suppose the model predicts how will you, but the correct value is how are you. So model predict that how will you, but the correct value is how are you. So what we can do here? So, okay, now since we said that model produces like one word at a time, the first word is how, because it's the most probable. Like it has a probability of 0.75, while other words have 0.03, 0.01, and so there are 10,000 such outputs. Uh, or suppose like if we consider that the dictionary is 10,000 words long. So the first word is like how, the second word is what, and the third word is you. Now we are going to feed these words back into the model. Imagine that it has produced like 10,000 such words. Uh, this model is going to give probabilities of all 10,000 words, which is the correct size of the dictionary. So imagine that this model is giving the 10,000 probabilities of all the words. So usually what we do is like instead of trying only for the best word, we pick the top three words here, and we call that the beam width, which is a configurable parameter. Like it can be three words, it can be five words. That totally depends on the person training it or the engineer training it. So let's say we pick the top three words and then feed these words back into the model, asking, tell me the next word after how. Then after what should I say? After you, what should I say? So again, like after how I'll pass a model, I'll pass the sequence to how. I'll also pass the sequence to what and to also to the you. So again, it will like give me 10 a probabilities of 10,000 outputs. We pick the top three again, and then again we continue the process. So if you look at it like it's like a branching process where the model is learning to pick and choose. Essentially, like this is similar to reinforcement learning, but not exactly. So you will like notice that ChatGPT basically learns from this. Like they train a separate model to pick and choose the right sequence and fine tune the selection of the last word. So this is essentially like beam search. I like hope it is clear to us. So like again, the output, how do we choose the sequence of output? So you basically like ask the model to give the next word, and when the model gives you the next word, you pick only the top three. Now you then pick the like most probable words from there and continue the process. Like when you're picking, you multiply the probability of the previous words with the next probability and pick the best ones. This way you get the most coherent and meaningful reference. Like in this case, if we see uh, the probability of how will is 0.75, which is the probability of how, into probability of will, which is 0.36. Comes at 0.27. Probability of how r is 0.75 into 0.32. So r is the probability of 0.32, and how is the probability of 0.72, which comes at 0.24, and so on. We just keep on multiplying the probability. So for next word, it will be probability of how into probability of will and probability of next word. So at last, whatever word is like whatever sequence is having the most probability, we just choose that. So this is the basics behind beam sets, that we just multiply the probabilities for each. So instead of just choosing the highest probable word, like suppose we chose only how because it's the most probable, then we chose will because it's the most probable. Instead, we choose n number of words, and n is decided by the engineer. So that's what happens in ChatGPT. Like when it produces the next word, it is producing one word at a time. Internally, what it is doing is it is generating the probabilities of 10,000 words. So like ChatGPT's vocab is not limited to 10,000 words, but like n words, whatever its vocab is, and like it's picking the one with the highest probability. Like since probability is what it is predicting, once you have the next word, it again feeds that previous word into the transformer and asks like, hey, give me the next word, and how this is how the process keeps going. So beam search is not the SE. Beam search is just an approximation of what they use. ChatGPT actually uses much advanced algorithm, and not only ChatGPT, all the LLMs use an advanced version of beam search itself. So that's why when if you have already worked with the LLMs, you would have seen uh, concepts such as temperature, top P, top K. So we generally like uh, we generally control the probability based on those parameters. So this is the beam search. Now comes the ChatGPT training part. So like training an AI model requires large amount of label data. Uh, However, like manually labeling data for every possible task is impractical. Like there are too many tasks and labeling is expensive and time consuming. So instead of relying on heavy supervision, we train models in a way that allows them to generalize and adapt with minimal label data. Like how does it exactly happen? To overcome this challenge, we like first train a model on a massive diverse dataset containing text from books, articles, and conversations. The goal is not to specialize in a single task, but to learn like general language structures, relationships, and context. This allows the model to capture useful patterns that can be transferred to new tasks. So here we are just so here like we are just understanding what what the language generally means. We are not training it for a chatbot. We are not training it for question answering. We are not training it for summarization. We are just teaching it what the nuances and the structure of the language. Uh, like Let me also introduce the difference between traditional machine learning and transfer learning. So in traditional machine learning, each task requires training a model from scratch, which takes time, data, and computing power. In transfer learning, we reuse knowledge from a pre-trained model, making training faster and more effective. So like instead of teaching a model everything from the beginning, we let it build on what it already knows, just like humans do when learning new skills. So what it exactly means is rather than training a model from scratch for each new task, we reuse a pre-trained model and fine-tune it for a specific application. Like the model which we train to generate to understand the structure of the language. So it now knows the language. It now knows the grammar. It now knows the structure. It now knows what each word actually represents. Now we can take this model from there and now we can fine tune it for a specific application. So like suppose we need to fine tune it for prepare it for question answering, we will just take that model from there. And what do we mean taking the model? We just freeze the weights of the model there and we take the weights from there, and then we will like further like prepare a data set on a Q&A, and we will like train the model further from that point only. So what happens initially, if we wanted to train for Q&A, we would have again like trained the weights from start. But now the weights are not trained from start. They have some initial value which they have learned during the pre-training. So during the pre-training, the model learns broad language patterns from vast amount of text. And then like instead of starting fresh, we take this trained model and repurpose it for different tasks. Like a smaller domain specific dataset is used to adapt the model to a specific application, improving its accuracy and relevance. Now that we have a model with general understanding of language, we can easily fine tune it for tasks like medical diagnosis, legal document analysis, customer support, and more, making AI impractical and scalable across industries. No, Prince, okay, Prince has asked, like, is it not a copyright concern? So no, it is not a copyright concern to take the model from someone else's model because most of the pre-trained model which we choose is open source. Like they are publicly available. Like there are so many BERT models, there are so many transformers model. So those are publicly available. The creator has given the permission for everyone to use it. So there is no copyright issue. So yeah. Now that we have now that we have understood the concept of training models with minimal supervision and fine tuning, let's talk about GPT. GPT, or like generative pre-trained transformer, is an NLP model developed by OpenAI. So it's built on top of the transformer architecture, but unlike the full transformer model, GPT uses only the decoder stack. Like when we, if we remember, the transformer consisted of an encoder stack and a decoder stack, but the GPT only utilizes the decoder stack. It did not include the encoder stack. This means like it generates a text one word at a time, predicting the next word based on the context of the previous words. This makes it highly effective for tasks like text generation, chatbots, summarization, and more. GPT is pre-trained on a large dataset which consists of common crawl web text. So this data is for GPT three, I guess. Yeah, yeah. This data is for GPT three. GPT four is even uh, GPT four is trained on even more huge dataset. So yeah. So the GPT architecture consists of a series of layers designed to process and generate text effectively. So first is the input layer, which converts the input sequence into embeddings, which then is the multiple transformer blocks. So as we know that there are multiple encoder blocks and multiple decoder blocks. So by multiple decoder blocks, by multiple transformers block, we mean multiple decoder blocks only. So these layers process the embeddings, applying self-attention and feed forward networks to build a contextual understanding of the input. So this is the so there are n number of decoder blocks. We generally choose it based on like the training purpose. Then there is the output layer. So this layer generates a probability distribution over the possible next tokens, allowing the model to predict the most likely next word in the sequence. Together, these components enable GPT to generate coherent and contextually relevant text one word at a time. The model can, after generating the probability, the model can then sample from this distribution to generate text, choosing words based on their likelihood within the given context. Uh, Again, it is the same diagram which we explained. That's the decoder part of here. So as we discussed, it follows only the decoder part of the transformer. So here we have the input embeddings, which is here, which are passed through multiple attention blocks. So here in the diagram there are six attention blocks. So this is first attention block which we can see, and then there are attention block two to six. So two to six will also have same thing, and same things happen here. We have value vector, key vector, and query vector. And we compute the self attention, and then we pass it to the feed forward layer, and so. So each step like refines the contextual understanding, helping the model predict the next one. Finally, the output layer generates text by sampling from predicted probabilities. The model is trained with specific objectives to learn a meaningful language pattern. The primary goal is text prediction. Given a sequence, predict the next word. Additionally, it can be fine-tuned for tasks like text classification, where it learns to assign labels to text. These objectives helps the model generalize these decoder blocks. Suppose these decoder blocks, these represent the pre-trained version of the thing. Now Now, these represent the pre-trained. Now this model understand the language. It understand the grammar. It understand the structure. So you can use for it for any task. So if you want to use it for text prediction, you will have a different output layer that will contain the output neurons of say one of n, where each neuron denotes the probability of one word. And if you are using it for a task classifier, it will only have two neurons in the output, whether one yes or no. In case it's a binary classifier, if it's a multi class classifier, it will be a different case. So, so once we have a pre-trained model, we can fine tune it for a specific task by structuring the input in a way the model can understand. Like as shown here, the classification task involves processing a single text input, while entailment task compare two sequences. Similar way, the similarity task evaluates how close two texts are, uh, and multiple choice task involves selecting the best answer based on context. By transforming input into token sequences, the model adapts to different applications with minimal modifications. So, yeah. After pre-training, GPT can be fine-tuned for specific tasks such as translation, summarization, or question answering by adding task-specific output layers and training on a small dataset, which I just told that only the output layer will change. So based on what this is the number of parameters of different parameters. So you can see that GPT-3 has more than 180 billion parameters, which is much more compared to the previous model Turing NLG, which had less than 20 billion parameters. So it's a very huge matter, and GPT-4 and GPT-4 is even very larger. Now to understand the like now we have understood how GPT is trained. Now we'll see how Chat GPT is trained. So, like, okay, what is Chat GPT if we see? So, we trained a GPT model and then we fine tuned it to for the question answering because Chat GPT is just a question answering chatbot. So that is what Chat GPT. And now, how did we that? How we did that fine tuning? Like we had a GPT model. So GPT model is the one which has understanding of the language structure, grammar, and the kind contextual understanding of the words and everything. Now, how we can fine tune it for question answering. So for that, we'll first have to understand reinforcement learning. So I'll not go deep dive into it. I'll just give you a brief intro about reinforcement learning. So in reinforcement learning, a software agent interacts with an environment. It makes observations, takes actions, and receives reward based on how good its actions are. And the goal here is to maximize rewards over time. The agent learns through trial and error, refining its strategy to get better outcomes. The method it follows to design action is called a policy. So suppose it predicts an action, and then you apply penalty over it. Oh, you are bad, so it will not do that again. It and then it again does a new action, and you tell okay now go, you have done good, and you give it a reward. So it will know that okay this is good, this is bad. So this is what exactly is reinforcement learning. So to make AI more aligned with human expectations, we use reinforcement learning from human feedback. ChatGPT first introduced this concept, but now it's used with by every large language model. So this process like defines the model beyond simple supervised learning by incorporating real human preferences into training. So the AI interacts with an environment, receives feedback, and continuously improves based on rewards from human evaluators. So what exactly it means? Let us understand. So before like reinforcement learning begins, the model undergoes supervised fine tuning. What I have already told. So human AI now humans come into play. So human AI trainers create example conversations where they play both roles, the user and the AI assistant. This step ensures the model starts with high quality responses before learning from real world interaction. Like, what do I exactly mean? So, like, a user will append a message that the user question is, how do I make a cup of tea? And then it will like again generate the response which AI should generate. So it will like generate a response like boil water, add a tea bag, sleep for a few, remove the bag, add sugar or milk if desired, or whatever. That so it will like give this pair. So this question answer pair it will the humans prepare that this is the question and this is the answer which we desire. So AI does not like learns exactly these words. It learns the pattern here. So like before generating its own answer in real world interaction, AI learned from these responses and like observe the pattern and then learn like how it should actually answer. So that's why if you see, so ChatGPT generally answers human in a natural language, like how normal humans do. So this is what exactly mean. So after pre-training, the model generates multiple responses for the same input. Like now we have like a to like now we have told it that you should generate for this question our answer should be something like this. So now we make it generate different outputs for same question, and then like for a one question how to make a suppose how to make a tea, it generates five different answers. So now there are human reviewers who rank these responses based on quality, accuracy, and helpfulness. So they will rank the okay. Rank two is good. Rank two is at the top. Rank three is better in this aspect. Like it gives us a feedback on each of the response. So this ranking data is like used to train a reward model that helps AI understand which responses are better. Then like after this the AI undergoes reinforcement learning using the trained reward model. So based on the human reviewers feedback, we train a reward model, and then we use it to train AI. So the AI generates responses, receives a predicted reward score, and continuously improves by optimizing its response to maximize the reward. So it will like okay, it will say that okay, response two is better, so it should generate more response like that. It will again change its weights matrices, and then it will like it just goes on the way of maximizing the reward. This is generally the image from the paper. So we begin by training the model with the human demonstrations to create a strong foundation. We begin with a data set of prompts. These are like real world queries or instructions, the questions which we generally ask. So we prepare a data set of that, and there is a human labeler which provides the desired response for each prompt, ensuring high quality outputs. So uh, think it from the start. This is training the chat GPT from the start. So we have the GPT like before this only we have the GPT model. We have a model which understands the language. Now how do we create chat GPT from that? So we like create some data set of input prompts, the input questions. Those are real world queries or instructions, and then a human labeler provides the desired response for each prompt, ensuring high quality outputs. This label data is used to fine tune the model, teaching it to follow instructions accurately and coherently. At this stage, the model learns from human example, but does not yet evaluate its own responses. Like it's learning from human example that yeah, I should answer in this way. So to sum up, we give it a question and answers, and tell it to learn from it. That this is the question, and for this is the expected response and everything. Now comes the second prompt. Like given a single prompt, the model generates multiple possible response. For a single prompt, for a single question, it will generate multiple possible responses. So again, human rank these responses from best to worst based on clarity, accuracy, and helpfulness. So whatever criteria they have decided. So these rankings are then provided to the like provided to our reward model. So reward model is the model which we train, which generally gives the reward model like we give this input to the reward model, and it will like convey that information to the chat GPT based on the format of reward. So this is what it actually does. So like a prompt like explain climate change in simple terms, the model generate like several explanation. Humans then rank them, and the reward model learns what makes a response better based on these ranking. So once the reward model like learns, okay, this is what exactly it wants. It starts giving rewards to ChatGPT based on the response it generates. So now that we have a reward model, I guess the reward model is clear. Reward model, like it's nothing complicated. It's just that it's a machine learning model, which we give a set of question and answering, which understand that okay, for this question, why is this answer better? Based on that, when it completes its training, when it completes the learning, we use it to train the chat gpt. So now chat gpt will not be interacting with us for the feedback. It will be interacting with the reward model. So reward model will give it reward based on the response it generated, and it will like fine tune its responses based on that. So now that we have a reward model, the AI uses trial and error to maximize its reward. It generates responses, the reward model then scores them, and the AI adjusts itself to improve. This optimization is done using PPO, which is an algorithm. So it fine tunes the model without making drastic changes that could degrade performance. Like we can make some changes, but if we make like much changes, then the architecture of GPT can also change. So that's what not we want. So that's why uh, we change fine tune the model. We change the weights, but only very little that they do not degrade the performance. We have now like walked through the complete training pipeline. So the this is how ChatGPT is trained. So like we started from supervised fine tuning to reward model training, and finally reinforcement learning with human feedback. And this combination of techniques allow the model to generate responses that are not just fluent but also aligned with human preferences. However, despite these advancements, the model still has limitations. Like in this case, if you see here, it confidently explains why an abacus is faster than a GPU. So because I don't know how, or it can also generate discriminatory results. Like write a Python function. So yeah, so it also has bias issue. There are lots of other issues also, such as hallucinations, or giving false info, giving hurtful sentiments, and like so many like if you consider Grok, which is the LLM designed by X, so they are currently using it for X. So it's they are not filtering any content, so it generally generates a very drastic responses, which is hurtful for a lot of audience. So I guess there's a little legal cases going on in that case, but yeah. So far, like we have explored the architecture behind ChatGPT from its foundation in transformer model to how it is trained and fine-tuned using reinforcement learning. We also discussed its capabilities and limitations, we giving us a deeper understanding of how it generates responses. AI model like ChatGPT are powerful tools, but they are not perfect. They require continuous improvements, better alignment techniques, and ethical considerations to make them more reliable and useful. That brings us to the end of our session. Now, I would love to hear from you. Like, do you have any questions? Feel free to ask before we wrap up. Also, one thing which I like to tell, we have also like this was just a brief overview of how everything works. Also, it did not include the code part of here. So we have also published a very detailed and beginner friendly blog on the similar lines. So I'll paste it in the chat. I pasted it in both the chats for that. So this blog takes everything from scratch, like how does a machine learn, and it has proper links to everything. So you do not need any prerequisites. How does model outputs a word, and it also includes several examples which are not possible to cover during a webinar. It contains more details such as RNA then transformers, and here we like explain attention in more detail by taking an example and complete like computing each thing, like how WQ WK looks, how attention score looks, what do we actually do, everything. And after that we understand the architecture in quite detail, like what each stack represents, and what is its input, what is its output. And then we also like code it from scratch using TensorFlow and Keras. We understand, we explain each code in quite detail. So this is a very deep dive, so which I would recommend everyone to go through. So yeah, that's all for now. Where are we getting the certificate for this session? You will be provided with the feedback form. Tejvi, can you provide the feedback form to in both the Zoom session and YouTube chat?
Yeah, just
Okay. On filling the feedback form, you'll get the certificate of participation and also the classes. Okay. So before we drop off, if you have any questions or confusions regarding the any concept, I would be pretty happy to explain. So yeah. So we have pasted the feedback form in both the YouTube chat and Zoom chat. Feel free to fill it and let me know of any. So before we wrap up, do you have any questions? Thanks, Veena. Thank you for that feedback. We coded the GPT architecture which completely. We did not coded that part like reinforcement learning and everything because for that we need a huge data set. So we coded the GPT part from completely, and we then gave also told the approaches of how you can take it further. So yeah. So if everyone has opened the feedback form, I can close the session because it will, on doing that, it will disappear. So should I do that? Okay, I'll be doing that. Okay, nice meeting everyone, and thanks for being here. Thanks for being in this session. I hope that this session was helpful for you, and it's so great to have such a lovely audience and uh, who asked such great questions. So we'll be wrapping up for now, and we'll surely meet in next webinars with new topics. I guess next we are planning to cover some more topics regarding reasoning models and how reasoning model works. So we'll surely get back on that. Okay, thanks everyone. Bye. Have a good day. I'll be ending the stream and I'll be closing the Zoom session.